Hello, everybody. Thank you for being here. I hope you can hear me well. If not, please drop a message in the chat. Thank you very much for attending this webinar lecture, which I already delivered in November last year in Florianopolis. I decided to give it again online, basically for the very reason that I wanted to extend these considerations, these reflections to a larger audience. And this is the reason why I am recording today the lecture, because I also want to make it available online in order to, as I said, to get more feedbacks. And the reason why I really would like to get more feedbacks is that here I am discussing something that I tried to think of and to discuss with myself and colleagues for a long time. And the idea is to try to promote also a collective effort, as you will see in the last slides, in order to improve our capability to estimate uncertainty of hydrological predictions. With a broader vision, I think that this also requires a rethinking of the way we frame hydrological models. I'm now sharing my screen. I hope that now you can see my presentation. I'm sorry, I erroneously muted my micro. So I hope you can see my screen now. The title is An Impossible Dream, the Deterministic Hydrologic Prediction. And the reason of this title is precisely the will to talk about uncertainty. Once again, if you see some problems with the audio or the video, please step in with the micro, because I'm not reading the chat at the same time when I am sharing the screen. By the way, your micro is open, meaning that you can open and step in whenever you want. I suggest that if you have any question to step in. I think we are not many people, so there is not the risk of getting into chaos. So first of all, this presentation is available for download on my website. In my website, actually, I am collecting everything is related to my research activity and my also teaching activities. So there is everything I do is there. Because I am a fan of open information, open education, open research, and therefore I am also including there the videos of my lectures, and I am including there my lecture notes and a copy of all my papers and softwares that I make available. And you can find in my website, just in the home page, a link to this presentation. It is the same presentation that I delivered in Florianopolis. Here, I will skip some of the slides, the more technical one, but anyway, you can find any detail that I presented there in this presentation here. So first of all, let's start with a couple of definitions, because when we talk about uncertainty, we also need to get into stochastics, into statistical description, because as we will see, I assume that the most classical way to deal with uncertainty, and the way I prefer, is through statistics and probability. So first of all, given that we are talking about deterministic predictions, what is a deterministic model? It is a mathematical model that with a particular input and an initial state, a given initial state, will always produce the same output. So there is no uncertainty. There is one point prediction. By the way, let me say that in hydrology, as many of you know, predictions are extremely important because predictions support our planning for the future. support the sustainable management of water resources and any resource that is related to hydrology. And predictions are essential also to cope with climate change, to devise climate change adaptation strategies, climate change mitigation strategies. So a deterministic model, as I said, produces a precise output. A stochastic model, I like this definition, which emulates the definition of deterministic model. A stochastic model with a particular probability distribution of input and a probability distribution of initial state will always produce the same probability distribution of the output. So we are not talking anymore of a point prediction. We are talking of a probability distribution, which means that the prediction is within a range. It's not precise. But on the other hand, this imprecision, this uncertainty is described in statistical terms, in probabilistic terms. And stochastic models are more common than we think. And even deterministic models can produce a stochastic output. For instance, in chaos theory is the theory that is supporting the analysis of turbulent processes. The models that we use for modeling chaotic systems are deterministic, but still they have limited predictive capabilities. And the reason is that even when we perfectly know the physics of the system, and even when we can perfectly describe the physics of the system, still the model may be not very precise in the prediction. And what is the reason? For instance, because we cannot measure the input variables and the initial conditions without any error. In these chaotic systems, even with a small error in these initial conditions, in these input data, produce a very uncertain prediction. So what I mean to say already now is that even when we have a perfect knowledge of the physics of a system, then still the prediction is not deterministic, is not precise. So let me describe the impossible dream. Let's suppose that at a prediction time, we apply a deterministic model to obtain a future prediction. And the deterministic prediction that we get, as I said, is precise. So it provides a prediction for a unique trajectory. So in red, the dashed red line is a unique trajectory. And the dream is an evolution of reality. The blue line superimposed to the red dashed line. It's an evolution of reality that perfectly matches the deterministic prediction. We know that this is not what we get actually, but the dream in principle may not look impossible because hydrology is described by the laws of physics, and so it's not subjected indeed to chaotic expansion. There is little chaos in hydrology. And in principle, in hydrology, we may obtain a lot of information on the input data, initial conditions. So the dream may not look impossible. And in fact, a large part of the literature insisted and is still insisting on trying to achieve this dream. But actually, what we see so far is that the outcome from the reality is something different from the prediction. There is a prediction error. And the prediction error means that there is a lack of deterministic predictability. And this is what I define as uncertainty. I define uncertainty as a lack of deterministic predictability. And also what we see is that the error cannot be predicted by the deterministic model. In most of the cases, really, the error is completely unpredictable. But let's look at the behavior of this error. Let's look in more detail. So the error, as I said, cannot be predicted. But actually, if we really look at it, at the time series of model prediction errors, we see that the error looks predictable to some extent. And thus, this means that indeed there is room for improving the deterministic model. And this is the target that the literature tried to seek for a long time. But what we noticed is that eventually, as far up to now, a part of error remains that is really unpredictable with the deterministic approach. And therefore, the latter can be defined as a random component. Random component means, once again, uncertainty, lack of predictability. So the presence of a random component means that the deterministic model at the end of the story is not correct. And this is what we know from our applications, of course. There is uncertainty. And this is why a large body of the literature tried to focus on uncertainty estimation. So what is the usual interpretation that the literature gives to uncertainty, the classic interpretation, given that we are working into mainly in the realm of physics? The usual interpretation is that the deterministic model is not correct. Clearly, there is uncertainty, so it's not correct. And we try often, the literature tried, several authors tried to associate uncertainty to lack of understanding, what is called also epistemic uncertainty. And therefore, several authors suggested to try to improve our models, to make an effort to improve our models basing on more precise data, basing on an improved understanding. And in many of the contributions, we read that actually the impossible dream is not impossible. With the refined interpretation and monitoring, maybe that uncertainty will be eliminated into the future. And if this came true, indeed, we would be able to achieve our impossible dream. But so far, this interpretation of uncertainty really didn't produce many results. And therefore, what I would like to also discuss with you is an alternative vision that is still knowledge-based. And the alternative vision, which was formulated by many other authors before than me, before than the current body of the hydrological literature, is to assume that uncertainty is an inherent behavior of our understanding of nature. And now I would like to call into play the famous discussion on quantum mechanics between Niels Bohr and Einstein, when Einstein stated that the famous quote, "He does not throw dice," he meant to say that he was not believing that quantum mechanics could only be described in statistical terms, because he firmly believed in the principle of physics, and therefore he wanted to say, I can't believe that in physics there is randomness. I fully agree, because indeed physics is regulated by deterministic laws, but I would say that still the world of nature is unpredictable. So how can reconcile a deterministic system with the unpredictability of the system? And this is confirmed by several evidence. As I said, our experience in hydrology, models for reproducing the hydrological cycle are inherently uncertain. And also our data are affected by uncertainty. And if you think to also the current interpretation of hydrology as a combined system, system between hydrology and humans, then when it comes to considering human behavior is inherently uncertain. So once again, how to reconcile this nature, this deterministic nature of the system that we study with unpredictability. So what I would like to support is a recognition that uncertainty is, as I said, an inherent behavior of the system. So it shouldn't be interpreted as a negative implication, but rather as an added value, an opportunity for improving our predictions. And to do that, we must realize that uncertainty does not mean that the laws of physics are not correct. Quite the opposite. we have to recognize that the laws of physics apply in terms of probability. And therefore, if we accept this concept, testing becomes more rigorous and more useful. And for instance, we can provide examples where validation of a physical law that fails in a deterministic setting may succeed in terms of probability. I will provide an example later on. So we have to recognize that the lack of deterministic predictability does not preclude that a process can be predicted in terms of probability. And indeed, these are very useful. But how can we do that? So in order to promote and support this vision, we need a theory. We need a theory that is translated into a workflow, that is translated into a model, and is translated into technical applications, because at the end of the story, we want to make prediction and use them. And therefore, we need to understand this relationship between the deterministic laws of physics and uncertainty. And of course, we need a model for uncertainty, which is not easy. This is why the body of the literature on uncertainty in environmental modeling is so large, because actually uncertainty in environmental modeling tends to refuse an easy and reliable probabilistic interpretation. And this is why the topic became so popular in hydrology, but in environmental modeling in general. So we have to find a way to reconcile these two, this vision, this deterministic vision, with the reality of uncertainty. First of all, let me say that we need to start from some conceptions. And first of all, let me say that uncertainty can be reduced. And for sure, reducing uncertainty is our target. Uncertainty can be modeled. Traditionally, it is modeled, as I said, by using probability and stochastics. There are alternatives. I will stick in this discussion on probabilistic modeling of uncertainty. And probabilistic description, yes, but it may include a deterministic component. Necessarily, it must include a random component. So we have to identify this model, which is in a way marrying, putting together the deterministic the determinism provided by physical laws with the random component of uncertainty. Let me just make a historical premise, an historical remark on uncertainty in physics, because this is a well-known subject. And I want to go back once again to the discussion between Niels Bohr and Albert Einstein. And the outcome of the vision of Bohr's on the interpretation of quantum mechanics, at the end of the story, at the end of this debate, became the prevalent view, and forms the root of the modern understanding of physics. Basically, in 1926, Bohr proposed that a particle's position in quantum mechanics was to be understood as a probability, without the possibility of providing a deterministic description. This is what I'm saying from the start of this lecture. And again, Einstein replied, I cannot really accept the idea that nature is governed by chance. He wanted to stick on the deterministic interpretation. But at the end of the story, as we know, the modern interpretation of quantum mechanics relies precisely on probabilistic description. Another, perhaps less known debate around this discussion was a debate in which the Austrian physicist Schrödinger proposed a paradox, again about quantum statistical mechanics. He too didn't want to accept this interpretation of quantum mechanics based on probability. And he made this thought experiment where a hypothetical cat, it is a thought experiment, is closed into a box for 1 hour, and its fate is linked to the random release of a lethal poison with a probability of 50%. So what Schrödinger said is that if we accept a probabilistic description of the outcome from this experiment, the cat may be both dead and alive at the same time. And he said, this is impossible. The output must be deterministic. The cat is either dead or alive. It's not possible that it is 50% dead and 50% alive, because this is not corresponding to the reality. And he wanted to question the statistical interpretation of quantum mechanics. But on the other hand, at the end of the story, the paradox turned to be supportive of the statistical interpretation of quantum mechanics, because it demonstrates, this experiment, that a deterministic prediction is not possible. It's really not possible. We can only provide a description in probability, which doesn't preclude the fact that at the end of the story we have a unique response, either dead or alive. But the chance of getting one of the two alternatives is governed by probability, and it's impossible to predict the outcome. I want to give another example, which I think it is very interesting, very well known, the Galton board. Suppose that you drop beads from the top of a vertical board with interleaved rows of pegs. So the beads are dropped and they bounce either left or right as they hit the pegs, and eventually they are collected at the bottom. And look, the physics of this system is fully known. However, if we try to fit a deterministic model to predict the position of each bead at a given time step, the solution will be for sure erroneous. So any deterministic solution will be flawed. On the other hand, a stochastic model assigning equal probability through a binomial distribution to left and right turn at each peg will deliver a perfect probabilistic prediction, which some of us know is given by the Gaussian distribution. So the knowledge of the physical basis and geometry of the system is essential in this case. So the physical knowledge is essential to assign probability to left and right turn. And this is the result. You see, this is an animation showing that indeed you get a Gaussian distribution. And it's almost a perfect distribution. It's not perfect because there is a limited number of bits that are released. But if you keep the experiment moving, you get to a Gaussian distribution. So the statistical prediction is perfect. On the other hand, as I said, and I want to stress once more, if we try to fit a deterministic model to explain position of each bead, the response would be mistaken. Okay, so let me give now a more hydrological and engineering-based example, which is related to a well-known discussion close to my home. They are in doubt whether or not to build a dam. And it's an example that can be fit into the realm of what is called socio-hydrology. So basically, this river provides irrigation water for the production of the Parmesan cheese. So it's an interesting experiment because you can understand the socioeconomic impact of the commercialization of the Parmesan cheese, and also it provides civil and industrial water supply. But historically, this river suffers from water scarcity. And I mean, the recognition of the problem dates back to more than 150 years ago. And therefore, given that there is a favorable condition for building an artificial reservoir, of course, this is a solution that has been long studied, but so far the dam was not built because there are several reservations. And in particular, the reservations are given by the fact that some people think that by optimizing water resources management, the problem can be solved. And on the other hand, they think that the dam would have a significant environmental impact. So there are three alternatives: no dam by improving water resources management, and two solutions for the dam, a big one and a small one. And the technical question is, what should we do in order to get to optimal water resources management downstream under climate change? Because of course now the concern is also reduced precipitation and reduced river flow. So this is a sketch of the system. Basically, we need an understanding of the future climate, and then we need an estimate of the crops and the water demands, an estimate of water resources demands overall for irrigation, civil use, and industrial use, and then we have to set up a model of the river system which allows us to test the various hypotheses, the three alternatives. And of course, we understand very easily that this is impossible to model in deterministic terms, at least because the climate scenarios are uncertain, and deterministic prediction of what the humans will decide in terms of solution is not possible. So what we need is a description in probabilistic terms. But now let me go back to my original question. How do we reconcile the physical understanding and the deterministic basis of the system with the presence of uncertainty? Now, first of all, if we want to embrace this mix, integrated modeling of physically based solutions with stochastic solutions, statistical solutions, we need probabilities of input data. So in this case, I listed the probability of the future climate scenario, probability for the river system, so probabilities of what the humans will decide in terms of alternative solutions, and other uncertainties may be included. So note, climate models usually do not include the stochastic components. They are based on ensemble simulation. So basically they estimate their range of uncertainty with ensemble simulation, which means that they use different input data, different initial condition. But let's take into account that ensemble simulation doesn't encompass all the sources of uncertainty. So you see that indeed, estimating these probabilities, it's not easy. And we have to find this possible solution, so combination of stochastic and deterministic components. There are several options for framing hydrological model in a stochastic setting. And the traditional approach is, for instance, to use linear models, the family of the ARIMA, FARIMA models. And then data-driven approaches are becoming more and more popular. And also these approaches can be physics informed, which means that we can include the physical knowledge. But on the other hand, you know, these solutions are somehow limited in taking into account the physical basis, in taking into account of the physical laws. We can also think of deterministic model with stochastic input parameters, including, for instance, models based on stochastic differential equations. We can think of deterministic models coupled with stochastic error models. One thing is important, whatever the approach, the validity of the stochastic interpretation of physical processes should be tested. And the validity of our estimate of uncertainty should be tested. This is very rarely done in many case studies. Estimates of uncertainty in some cases are provided, but they are not always validated, tested, okay? Here, I want to discuss possible solutions which are based on some contributions that I presented in the past 10 years, because, as I said, it's a long time since I started trying to better understand how to optimally combine the deterministic nature of hydrological systems with their random component. And in particular, I want to start by recalling the contribution on stochastic physically based modeling to introduce the concept, the contribution that I proposed with Dimitris Koutsoyanis in 2012. Basically, this contribution, which may look a little bit complicated to if one looks at the theory. Of course, we need to support our conclusion with the theory. And unfortunately, the theory of statistics, sometimes statistics and probability, is a bit cryptic. But actually, the essence of the contribution is very simple. So I want to make an attempt to explain it also now in very simple terms. So what is our objective? From a deterministic model on the left, which gives a point prediction. Q is a point prediction. S is a deterministic model. Theta is the parameter vector. X is the input data vector. Here, if I give precise values of parameters and input data, I get a point prediction with no uncertainty. So we want to move to probability distributions. So probability distribution FQ of the model prediction, which is expressed depending on the probability distribution of parameters and input data. This is what we want to do. And what we concluded is that it's very simple to do that. What we have to do, and forget about the double integral and look only at the argument of the double integral. What we have to do in order to estimate the probability, left-hand side, probability distribution of a model prediction, FQ, is to multiply the probability of the parameters, the probability of the input data with the probability distribution of the model error. So if we multiply these probabilities, we obtain the probability distribution of the model prediction. So what I need is a probability distribution of the parameters, a probability distribution of the input data, and a probability distribution of the model error. The double integral is just a summation. I have to extend this multiplication over the whole space of possible parameters and input. And in order to extend this multiplication to the whole space, I sum for different value of parameters and input data the respective probabilities, multiplication of probabilities. What is the key step here? Is the definition of the probability distribution of the model error. And this is what is somehow missing in ensemble prediction. Many models are estimated their uncertainty with simply making ensemble prediction, so several prediction for several parameters, several input. This is what is done here, but here there is an additional term, an additional factor. It's the probability distribution of the model error. And this is the key step that many methods for assessing uncertainty are missing. This is the way of introducing the random component. So the deterministic model may be the best one, but still has a random component, as we discussed. And this random component has to be defined in terms of a probability distribution. And this probability distribution is the probability distribution of the model error. And from an operational point of view, is very simple. So here is the same equation, upper left. So we pick up an input data vector from the input data space, X. We pick up a parameter vector, and then we run the deterministic model. But we have also to add one realization of model error from the related probability distribution. If we repeat it many times, we obtain the probability distribution of the output. So again, if we drop the addition of the model error, it is the classical ensemble simulation for different input data, different parameters. If we add the model error, it becomes stochastic, physically based modeling. And here then, as I said, the key step is the probability distribution of the model error. And the literature proposed several alternatives. ARIMA modeling, linear models, to describe the probability distribution of the model error. There is the problem that linear models are based on the Gaussian assumption, so you have to preliminarily transform the data. There is, I think, a very interesting approach, the meta-Gaussian approach proposed by Christophovis about 20 years ago. It was very popular. It has been very popular for about 10 years, and then today is forgotten. I think it's very interesting, again, to describe the output of a deterministic model in probabilistic terms. Simulation and resampling methods. There is glue, ensemble simulation. I'm not convinced it's exhaustive, but still, several contributions sticking on it. modified meta-Gaussian approach, which is the one that it was used by me and Dimitris Koutsouyanis in 2012, and also data-driven approaches to describe the model error. And there is, I think, an interesting contribution by Anna Sikorsky in 2015. And now I want to focus on a data-driven model, which we recently proposed again with Dimitris Koutsouyanis, Blue Cat. And here under review, fortunately, the paper has just been accepted. And there is a first paper proposing Blue Cat in 2022, and then a second paper also proposing making available the software. So let's try to understand a little bit more. Give me a few minutes to describe what is Blue Cat. And basically, it's a method. Okay, let's forget about the acronym. I'll explain to you why Blue Cat. It's nice, at least, or in our intention, wanted to be nice. And so basically, Blue Cat is a method to transform a point prediction from a deterministic model into a probability distribution, and it is data-driven. And it is more than just an uncertainty assessment method, because in doing this transformation from deterministic to probability distribution, it also introduces a bias correction. Let's see how it works, because again, it's extremely simple. So basically, we can make a point prediction obtained with a deterministic model. Of course, we have to make an attempt to use the best possible model, the model with the most limited uncertainty. And then we look at the calibration time series of this model, because Blue Cat is applicable only to calibrated models so far. So we need a calibration time series, which means a time series of past predictions and corresponding reality. So we look at the sample of neighboring to the prediction, neighboring in magnitude, simulated river flows from the calibration period. So once again, I issue a prediction for a future variable. I take the value of this prediction. I go to the calibration time series, and in particular to the time series of the predictions, and I identify a sample of neighboring predictions in magnitude. And then I can form a corresponding sample of observed reality. So I take the neighboring past predictions, and then I form an observed sample of the corresponding reality, because they were past predictions, so I know the reality of the past. And this sample of reality corresponding to past prediction is used to estimate from data the probability distribution of the future prediction. So once again, I go from a prediction to the calibration data set. I get the closest predictions in the calibration data set. I take the corresponding reality, and the corresponding reality provides to me a probability distribution of the predictant, from which I can estimate the mean, and therefore the best prediction, which is corrected already, and the confidence band. Let me give you a sketch. So if this is my prediction, I start from the forecast time, and the blue line gives to me the deterministic forecast. If I only made ensemble simulation, I would generate around here an envelope. If I apply Blue Cat, there is a bias correction, and then the generation of an envelope. And how is generated this envelope? By looking at the closest realities in the calibration period. So this is very easy. Of course, it is based on assumptions. And what are the assumptions? First of all, we need to understand that everything is stationary, going from calibration to prediction of the future. We know that this assumption may be questionable. I mean, we could remove this assumption. In the current version of the method, we prefer to stick on stationarity because it is more robust. Now, there is a key assumption. The calibration data set needs to be long enough. we proved with our papers, our studies, that if the calibration data set is long enough, indeed, the upgrading of the model, the uncertainty is estimated in a reliable way. Look, we don't subdivide uncertainty in different components. There is the literature sometimes tries to split uncertainty into epistemic uncertainty, inherent uncertainty, input uncertainty, parameter uncertainty. We don't like splitting uncertainty into categories because we think that this splitting is not very robust. So we just look at the model error in calibration, and by looking at the model error in calibration, by looking at the prediction errors in calibration, we estimate the uncertainty for the future predictions. So why Blue Cat, first of all? Okay, there is an explanation for this acronym, but actually we decided the name first, and then we found the corresponding extended title to justify the acronym. Blue Cat refers to the pop-up, to the pop art by Andy Warhol, a success creation stimulated by a very simple idea. And this is what we are trying to achieve. So a transformation of a deterministic model into a stochastic approach in a very simple way, by simplifying it as much as possible, because simplicity in our interpretation is equivalent to robustness and to reliability. Also, the Blue Cat gives an idea of positive thinking and optimism, which is also the attitude that we try to assume, because of course creativity is supported by positive thinking. There is a theory for Blue Cat, but I would skip this slide. As I said, the theory is necessary. It's not particularly complicated, but on the other hand, I hope that you understood in technical terms the workflow, and then the theory. I don't think it's needed now. One important thing. Testing, I said, whatever method we use to integrate a deterministic model, to formulate a deterministic model in a stochastic setting, we should test it. And the optimal way to test, in my opinion, is to check that uncertainty is well estimated. We proposed an open software. I'll give you the reference for Blue Cat, and the software automatically performs several different tests, starting from the simple ones like scatter plot of observed versus predicted data by the deterministic model, by the combined deterministic plus stochastic. And I think it is a very powerful method to understand if uncertainty is well estimated, is what we call predictive probability plot. Let me just focus a little bit on it, because I think it is very interesting. And what this method does is to look at the position of each true value of predictions into the confidence band for a long series of predictions. So once again, I look for a long series of predictions, the position of the corresponding reality inside the confidence band. And of course, what I expect is that if the confidence band is estimated at the 90% confidence level, I expect that 10% of the points are outside the band. And I also expect that the points that are inside the band are distributed according to precise probabilities. And this plot compares the probability of finding each point into the confidence band given by the theory with the reality of what we observe during testing. It is very useful because if you get a straight line, it is perfect. If you get narrow bands, you get a behavior of the plot like the blue line. Large bands, too large, of course, it's not good if the bands are too large because uncertainty is overestimated, correspond to the green line. Systematic overprediction corresponds to the orange line, systematic underprediction to the pink line. So if I go back, you see here this behavior means that in this specific case study, we got into a little bit narrow band. And I'm not going into the detail, but if you measure the distance between the quality line and these narrow bands, you can also quantify how much the band is too narrow. I think it is extremely powerful. It's not our idea. It was first proposed by Lion Tamea and then discussed by several authors, but strange enough, it's not popular. Perhaps because it's too rigorous, maybe. Okay, so I just want to say that in the paper that was just accepted, we also apply BlueCat to multimodal simulation. So simulation with many models, it's possible. It is straightforward, and we provide a software for it. It's on GitHub, and here you can see the references. You can download my presentation from my website and get these references. And then I think it's time to come to my practical and active, creative proposal of cooperation. So what I really would like to do to further explore these topics is to study what are these reasons of uncertainty from a real world point of view. So what is originating uncertainty? If uncertainty is an inherent behavior of this physical system, there must be a physical explanation for it. And this, I think, would give us the opportunity to better describe uncertainty. And at the end of the story, to really improve our capability of make predictions, especially with respect to ungauged catchment. And in particular, what I would like to study is what are the conditions leading to what I call climate impact amplification, which means a step change, in the impact of flood and droughts triggered by a minor change in climatic drivers. And the assumption is that there must be the occurrence of critical conditions that suddenly originate a surprise event, something that really we don't expect. And I think that understanding uncertainty gives to us enough support to understand also surprise, to understand when there is this amplification of impact. And I would like to explore this topic, this subject with I was lucky enough to get a project financed by the Italian government. And the first step that I want to promote is a collection of events. And I published a public call, which I am also now trying to make visible on the social. And here is the reference in my website for it's the web page of the project. A public call, as I said, for events that took communities by surprise. And the first aim is to try to identify why this event caught the people by surprise by assembling a global inventory. And of course, surprise may be originated by a rainfall event, a precipitation event that was really unexpected. So in this case, the reason for the surprise is unexpected climate. But there are many other cases where the reasons are more than one, and not only climate. Of course, for an extreme event, there is the root of an extreme hydrological event is a climate extreme. But there are indeed cases where a moderate extreme in climate generates a very impactful event. And the first step to better understand, I think, is a global collection of case studies, a global map. And of course, the reason of the surprise may be climate, may be hydrology, may be land use change, may be river training, may be something related to socioeconomics. So if you are interested, I really would like, one of the purposes of this lecture is to try to involve colleagues in contributing to put this inventory of case studies together. We already have several databases that were suggested to us. but I really would like to promote a collective effort in order also to get different interpretations and consultations. And the idea would be to start with a paper describing just these events and what happened without any attempt to modeling up to now. So basically, a take-home message, and this is my last but one slide. Okay, basic assumption, the world of nature is unpredictable, and the world of nature is dictated, is governed by deterministic equations, but still it is unpredictable. And so what we need to do is to embrace uncertainty in my interpretation, but I really would like also to get your feedback, not necessarily today, because today we are already a bit tired, and embrace uncertainty as an inherent feature of hydrological models. And this has a relevant implication in communication and policy making. I think that if we turn it into interpretation of uncertainty as an inherent behavior, I think this implies a change also in our communication and policy making. And the way that I so far explored is physics-informed stochastics to interpret randomness and understanding predictability. And also I want to stress once again the importance of testing. Before I move to the last slide, please take into account that I am willing to get questions. No problem if you don't have any, but I will remain also connected, and I really would like to get your questions. Last slide. We have a conference in Bologna on June 1920, and the conference aims to discuss these issues. It's a Leonardo conference sponsored by EGU and also sponsored by an Italian foundation that is now trying to put together a collective effort to study solutions for mitigating environmental risks. The title is From Science to People, Expecting the Unexpected in Flood and Drought Risk Management. The abstract submission is already open. And here I don't have the reference of the website, but if you go to Google and you look for 2025 EGU Leonardo Conference, you find it. And in any case, if you don't find it, please do send me an email. Abstract submission is open up to March 31st. Okay, let me share the screen and let me stop the recording.